All right, so let's look at another example of using drag forces here. So this one is actually a combination of the two examples we actually did before this. So basically vertical motion and horizontal motion. But in this case, what we're going to do is we're going to paste those together and look at something which is a two-dimensional motion. So something that we remember from 205, more specifically projectile motion. So basically, we want to see now what would happen to an object under projectile motion or parabolic motion if there was some sort of resistance. Right? So now we're going to have some sort of air drag, which is acting on the system. Now, to simplify our lives a little bit easier, make it a little bit easier in this case, we're actually going to look at simply a linear air resistance. Otherwise, as we mentioned previously, if we have the quadratic case, we end up with the magnitude of the speed, which means that the both different directions are actually coupled with each other. And you'll see that in the homework as a numerical case. So in that case, we actually have to solve it numerically. But here we're going to do it as an example in linear, so that way everything's actually uncoupled in this case. So again, so let's go back to physics 205 for a second. And let's think about what happened with the range equation with projectile motion. So let's say here was my object, starting off here, give it some initial velocities. Green, so there's my initial velocity. This guy's on an angle of theta initial, and then this guy is going to go under projectile motion. So it's going to do something like this, right? What we said in 205 is that this thing is completely symmetric, so it's the same on this side as it is on this side. Hence the name projectile motion or parabolic motion, because it just creates a parabola. And then in this case, what we know is that it starts and finishes on the same horizontal line. So let's remind ourselves of what the range equation says. So actually write that here. So in this case, we would look at what our components. So we would look at the x component here. We would look at the y component. And then in this case, in the x direction, according to my coordinate system, I get x then is equal to v initial x, which is the cosine portion. I'm just going to write it as the initial x times t. In the y direction, we get the y is equal to y initial, which is 0, times the initial y times t minus 1/2 gt squared. And again, t, or not t, but g we know is downward, so that's going to give us the negative here. In this case, then, since we know it finishes and starts at y is equal to 0 along the same horizontal line, we can then say 0 net is equal to v initial y minus 1/2 g times t must be equal to 0. Now, in this case, of course, this thing is equal to 0 when either this t here is equal to 0, which means that we'd actually be looking at here. So this would be when it's at the initial position, which can't be true, which means we then have to set the parentheses here simply equal to 0. So in this case, we get t then is going to be equal to v0y divided by 2 times v0y divided by g. Yeah. So in this case, this is when it hits the ground, and we know in that case, if I put it in here, that's going to give me the range. So here I would say the range then is going to be equal to 2 times the initial x times the initial y, all divided then by g. So this is what we call the range equation. I'm going to leave it in this particular form here instead of using my angle formulas, my double angle formula. Oh no, a double angle formula. 2 times the angle formula. Yes, double angle. And then just leave it this way. Right. Now, this again this is what happens when it's in vacuum. So this is then going to be our vacuum solution. So things don't actually have any air resistance to it at all. So again, this thing is completely symmetric. So this means that again, the distance that this thing travels is that distance of r. It's the same on the one side as it is on the other side. And this is our vacuum range. So for now, I'm going to call that guy r sub 0 for the vacuum. So basically, we want to do the same thing now, except now we're going to add in air resistance. All right. So what did we find last time? So basically, last time we found that in vertical case, it was a little more complicated, but we see that it has the air resistance acting onto it. And then in the horizontal case, so ultimately, what we would think then is what our expectations here. What's going to happen to this thing if it's then moving in air resistance? So in this case, I would then have this scenario here. Draw straight. So this is my x direction, this is my y direction, and let's start off the same thing. Here's my object, starting with some initial velocity. Here's my v initial at the angle thing initial. Now in this case though, instead of going under parabolic motion, which again is symmetric on both sides, this thing is actually going to become skewed. And the reason for that is what? As this thing is actually moving under its parabolic motion, it's going to feel that drag force acting on it in both directions, causing it to slow down more quickly in both the x and y direction, which means that it's going to taper off, reach some sort of max height, and then it's going to fall something more like this, right? So in this case, we can see that what? It is not going to be symmetric. Which means if I cut this thing in half again, it is non-symmetric because this side over here is different than what it is on the other side. So this thing is non-symmetric. As opposed to, again, the other case, which is going to do something more like this. Good. So in this case, we would expect then that what the distance that it travels, let's call this guy R, versus the distance it travels without air resistance, which we just called that R0, is then going to be less, right? So our expectations in this case then is that, well, the physical range at which this thing travels has to then be less than the actual vacuum solution, right? So this is our expectation. So good. So basically, let's determine what the actual range of this thing is going to be. Now, to do this, basically all I'm going to do is I'm going to use our results from the previous two examples and basically just paste them together. So we're just going to go back and pull off the solutions that we need by doing the same thing we just did. So basically what we're going to do is we're going to work with the x components and we're going to work with the y components. So same thing as before. So if we go back into what we had previously did, we can actually just read off what these things are. So in the x direction, again, using an x initial is equal to 0, I get x then is equal to m b initial x divided by b1, where I get b1 is the drag coefficient, times then 1 minus e to the minus t divided by m. And then in the y direction, we then have that what? Y was equal to minus mg over b1 times t, plus m squared b over b1 squared, times then 1 minus e to the minus b1t divided by m. It looks like I'm running out of room over here, plus v initial y m divided by b1 times 1 minus e to the minus b1t over m. So these are my two different directions and just lifting again off of what we had previously done before this. Now, in this case, we're going to do things slightly different. So in this case, instead of using the y component to find the time and plug that into the x direction, we're actually going to use the x direction to find the time. Just a little bit backwards. So let's go ahead and do that. So basically, what I'm going to do in this case then is use this one to find what is the time for any particular x value. So basically, all I'm going to do is solve this guy for t, and then we'll put in the fact that we wanted to go the total distance bar. So let's do that. So let's solve this for t. So solving this for t, we would then get is that t then is equal to m divided by b1 times the natural log of then m b initial x divided by m b initial x minus b1 times x. Now here I'm going to simplify a little bit. So I'm going to divide inside by m the initial x, so that this thing will finally become then, and then pulling out a negative sign, switch the two of those, I get minus m b1 times the natural log of 1 minus b b1x divided by mb0x. Right? So negative sign again comes from the fact that I have a natural log of say a divided by b, which is then equal to minus the natural log of b divided by a. So that's just negative of that. Right? So great. So this is then going to be the time it takes to get to any random x position. So now let's take that time and let's plug it into the y expression. So now what I want to do is take that time and then plug it into y. All right. So good. So let's go ahead and do that. So in this case, then I can do what? So let's take that time and plug it into the y. So let's go ahead and do that. So again, reminding myself what y was. plugging that in, so I then get y then is equal to, do some because I forgot already. So this is a minus mg divided by b1 times t plus then m squared g divided by b1 squared times then 1 minus e to the minus b1 t divided by m plus v initial ym b times 1 minus e to the minus b1 t over m. Good. So let's look at this guy. So now let's put in this t here. And I'm going to simply plug this guy. So this is now going to become what? So I'm going to go plus, so it's going to become an m squared g over b1 squared times then t, which is then the natural log of 1 minus b1 x divided by mb initial x. So that's the first term. Second term then is going to become plus m squared g b1 squared times. So I'm going to get a 1 minus. So notice what's going to happen here is that what? So notice that I have a b1 over m inside of the exponential as opposed to here in the time I have an m over b1. So those are actually going to cancel with each other, and the negative sign is actually going to cancel, which then gives me a positive sign, which means I have an e raised to the natural log, but e raised to the natural log is the same thing as simply the argument. So this then is going to be times 1 minus b1x divided by m initial x. And so that's that term. And then I get a plus b initial ym divided by b1 times then the same thing, 1 minus b1x divided by mb initial x. Good. So let's start canceling some stuff here. So basically this term here is going to cancel with that one, and then this is going to make this guy a positive. This is going to cancel with this one, which is also going to make this guy a positive. So let's plug that in. So finally, I'm going to get a m squared g over b1 squared times the natural log of 1 minus b1x divided by mb initial x plus m squared g over b1 squared times then b1 times x divided by mb initial x. I'll cancel the terms here in a second. Plus b initial y m over b1 times then b1 over m times x b initial x. Good. So let's cancel some terms here. So this b1, of course, is going to cancel one of those. This m is going to cancel one of those. Here, this n cancels that one. That b cancels that one. Okay. So good. So let's finally simplify and pull some terms together. So what I finally get then is that what? Y then is going to be equal to x divided by v initial x times v initial y plus mg divided by v1 plus then m squared g divided by v1 squared times natural log of 1 minus v1 x divided by mb initial x. So this, what is this? So this is y then at any given x position. Right? So basically, to go forward, now all we're going to say is that's what. So let's note that when x is equal to r, which is the final range distance that this thing is going to make it, this thing has to have hit the ground, which means y then must be equal to 0. So basically, by the time this thing has reached the distance of r, this thing has to be back down to the ground, which means that we know y then must be equal to 0. So let's go ahead and do that. So let's replace all of our x's here with r's, and then set this thing equal to 0 because that's what y is equal to. Let's do that. So I get a 0 then is going to be equal to r divided by the initial x times then the initial y plus mg divided by b1 plus m squared g divided by b1 squared times then the natural log of 1 minus b1x divided by mb initial x. I'm sorry, that should be r. Now, to determine the range then, basically all I would then have to do would be to solve this expression. Now, of course, that's easier said than done, and the reason for that is, this is very similar to one of the problems we saw last time, is here I have a linear r, but here I then have an r inside of a natural log term, right? Which basically means that I would have to now solve for a linear r in a natural log of r, which is something I can't do in closed analytical form. Just doesn't allow me to. So what I'm going to have to do instead is either solve this guy, say, numerically for certain set conditions on what the initial velocity is, and etc., or I can make some sort of approximation. Now, basically, what I want to get a feel for again is how much shorter is R versus R0. Again, this is the vacuum solution. So, I mean, I don't really want to just randomly pick numbers and then numerically solve this. So let's look at a approximation of this. So let's look at an approximate solution, just to kind of get an idea of how this thing actually mathematically kind of works out and where all the pieces kind of fit together. So let's look at our approximate. So to get an approximate solution, basically we want to get rid of that natural log. And the best way to get rid of the natural log is, well, the exponentiate, but that's not really going to help us. So in this case, what we want to do is what? Do a Taylor series expansion on this guy. So to do that, what must be true then is that b1 times r divided by m, the initial x, much less than 1. If I knew what it means. There we go. So basically, we want to look in this region and treat this guy as a small parameter. So that way we can actually do a Taylor series expansion of the natural log. So let's do that. So in this case, let's do a Taylor series expansion about that guy. So this thing then is going to be 0, approximately that equal to r divided by the initial x times then the initial y plus mg over 1 plus m squared g divided by b1 squared. Now in this case, what we're going to do is we're going to take the Taylor series expansion of the natural log here, and we're going to take it up to order 3. Okay, so I want to expand this guy all the way out to r cubed. So in this case, I can look up what the Taylor series expansion is, and what I get then is that this thing is going to be equal to, so if I call this guy, say, x, so let's find this guy, and x, what's another parameter? We'll call it alpha. So basically, this thing is going to go as alpha. So this is going to be my alpha. So I get a b1r divided by m, the initial x. And I get plus 1/2 of alpha squared. It's going to be a b1r divided by m, the x squared. And then I get plus 1/3 of then alpha cubed. So that becomes b1r divided by m, the initial x cubed. Now, of course, there are higher order terms, but I'm only keeping the cube terms basically for a reason, and that's mostly just to cancel out other terms and see where that actually comes from. So let's multiply all this stuff out. So in this case, I'm going to get a what? The initial y divided by the initial x times r. Good. And then I'm going to get a plus mg divided by b1 times r. And then I get a plus. So let's start killing off some terms here. So this is going to give me an m, because in this case, this m here is going to kill off 1 from there, and that b is going to cancel off 1 from there. So this guy is going to be equal to mg divided by b1 times r. Oh, sorry. I need a negative sign out front. That's Taylor. So this comes in with a negative sign. Negative, good. And then I'm going to get a what? So now the next term, so it's going to give me a minus 1/2. So in this case, the m squareds are going to cancel, the b1s are going to cancel. So I'm going to get an r squared divided by the initial x squared. So that's going to be that term. And then I'm going to get a minus 1/3. And then here the 3's. So I'm going to be left with an m on the bottom, a b1 on top, a g on top. And then I'm going to have an r cubed divided by the initial x cubed. Okay. So notice that what basically happens then is that this term here is the same as this term, so that's going to cancel out, and then I'm going to be left with just some other terms. Okay. So good. Now from here, what I'm going to do is I'm going to multiply both sides then by a term just to reduce this a little bit better. So I'm going to multiply this by 2v initial x squared divided by g times r. So that this thing is then going to simplify to, once I solve for r, again, r then is going to be equal to 2v initial x, v initial y divided by g minus 2/3 of then v1 divided by mv initial x r squared. But again, we can easily identify that this thing here is actually just our vacuum solution of R0. So then this is going to be equal to R0 minus then 2/3 then V1 divided by M the initial X times R squared. So basically, comparing this thing, we can see then is that, yes, what's going to happen then is that the range of this will be shorter because, again, R then would only be equal to R0 if this term was then equal to 0. But also, remember what our small parameter is. That's B1R divided by MB0X. So this is a B1R divided by MR0X, which means that this is actually a very, very small term. So ultimately what happens then is that indeed the range is going to be less, but it's going to be less by a small amount, at least in this case, because we're doing a Taylor series expansion. What I know is that this distance here is going to be very small because again, B1R divided by MBX we know is much, much less than 1. So it will be less, like our expectation said, but not by a very large amount. At least in this case. Now, again, if I was looking at a much bigger, say, damping parameter in this case, so that D1 was, say, much, much, much bigger, in this case, it's going to be less by a much greater amount because the size of this term here is going to get much, much, much bigger. Now, again, this term is only technically true because of the Taylor series expansion, but again, you can imagine that this term then is going to grow, which is going to make this thing fall even shorter. So ultimately, again, all this means is going back to our picture that yes, this thing is not going to travel as far. It is going to taper down and it's going to look something like this. Probably not as extreme as which I drew. It's only in the case where B1 becomes much, much bigger. But this is matching our expectation. Good. So this is then the range equation, but again, using the linear acceleration to look at how this thing is actually decreasing over the range at which it travels due to this linear